Yeah, it was kind of expected, but what you can say about 420 to just get started on the last day on Friday. Okay. We'll do that probably in Norway and Minnesota as well. So slightly different version because we make progress almost on a daily basis. But so should we get started, folks? I just need the signal from them. So. Okay, so welcome to distributed tracing using OpenCensus. And I would like to start from the Lehman law. So Mayer Lehman was the professor here in Imperial College in London, and he formulated a set of laws about software evolution, later being called Lehman laws. One of his laws said that the change in software is inevitable, and the software is going to change no matter what. It doesn't really depend on the bad design or bad implementation. It's just that the software naturally has to evolve, and as a result, it has to change. So it's not surprising that in the last 20 plus years, we were seeing revolution in software and in hardware. If previously we were running our code on premises on dedicated hardware, now we do it on the cloud. We were running on virtual machines in the cloud, but today we kind of move towards containers world so that we reduce the footprint of our workloads and improve efficiency. We were running monolith applications which were deployed as a single unit and were really hard to scale. And today we tend to develop more in the microservices style, which means that every microservice could be developed by a different team and deployed separately and scaled in a much more efficient way. We used to develop using a single stack, single language, and today it's much more common to see services where you have Go, Python, Java, and some other languages mixed together because multiple teams could create software using different languages of expertise. And so we see polyglot services. We used to run things in the single cloud, but today actually many companies are looking for moving into multiple cloud solutions for redundancy and making sure that their applications will always work despite the outages that could happen from time to time. There is even a second layer of evolution where we move from the containers world into the serverless world, where we don't need to focus on how to run our infrastructure, but we mostly focus on the actual function that we want to implement, and somebody else takes care of the infrastructure. Now, with all those new architectures and the new evolution come also new challenges. How do we debug software in this new world? How we detect problems, and how do we understand that the problem has happened and what that problem could be? How do we develop? Maybe our development practices should change as a result of this evolution. How do we package the software? How do we deal with secrets and configuration management? It's a lot of problems, and obviously I can't cover all of that in one lecture, so we'll try to focus today on observability. And before we delve into that, I'd like to introduce myself. So I'm Simon Zeltser, software engineer working on improving developer experience with infrastructure and operations products in Google Cloud. So observability, what it is. I think the easiest way probably to define that is being able to debug the system and gain insights into the system's behavior. Now, some folks think that observability is just a new way to say testing or to say monitoring. Every couple of years, we tend to invent new terms, and we try to kind of give new meaning into the concepts that we already know. But that is actually not true. And Cindy Sridharan came up with a really nice Venn diagram that illustrates that observability, it's not just testing, and it's not just monitoring. It's about understanding the root cause of the problem on every single stage that this problem could happen. Before we deploy the problem, so we do some testing. Also after we deploy, so we can run some monitors to detect predicted failures. All of those things are covered in observability, so it's not just a new word. Now, Baron Schwartz, he's very known for his contributions to MySQL. He once said that monitoring tells you whether the system works. Observability lets you ask why it's not working. So I think if you remember that, it will give you a really good picture of what we are going to talk about. Now, with observability, we usually want to take the holistic approach. We want to gather all the signals that could be available for our systems and put them all into the single timeline, be it logs, metrics, traces, profiling information where we can just profile the system for CPU and memory allocation for every method that gets executed as part of our code passes. So we just want to take all the signals, put them together on the same timeline, and then get some meaning out of that. Now, what if I told you that there is ultimate recipe for making your cloud services reliable? Something that will always work and something that will always make you successful. So it's just three things. It's very simple on paper. Track system health, detect problems, and then fix and refine, basically rinse and repeat. It's this cycle that never ends, but at the same time, it's just the three simple things that you need to take care. But guess what? It's just like a gym problem. So some people know that if they want to lose weight, they go to gym. They need to practice at least 3 times a week, probably lose some calories, eat healthy, and the results will come. But apparently, it's not that easy. So apparently the problem of observability is a hard problem, but it's also an expensive problem to solve. You need to deal with things like context propagation, multiple environments, external dependencies, vendor locking, which kind of forces you to only use what the vendor has to offer and you can't move out. And of course, cost could be an issue as well. So OpenCensus is our try to get these problems to resolution. OpenCensus is a single distribution of libraries in multiple programming languages that allow you to do metrics collection and traces collection for your systems. It's a single set of APIs, which is implemented in 8 languages at the moment, including .NET Core. My examples are going to show C#. But it's also available in other languages as well. Sorry. So digging a little bit more into that, it's a single set of APIs for metrics and traces collection, which is implemented in idiomatic way in every language that's popular today, be it Python, Go, Java, C#, and so on. It has a lot of integrations with external systems, such as, for example, if you use Redis cache and you want to gain some insights into what is happening as part of the incoming requests into your system, such that that request could trigger some activities on Redis. You want to get some insights into what's going on, so OpenCensus kind of provide some integrations which allow you to get that visibility without writing any additional code for that. It also implements the context propagation. We have some proposal for how to do it in a way that's being standardized across the industry. So this context propagation is implemented across all different languages and all different packages that we offer in OpenCensus. And it's also a set of exporters which allow you to take all this observability information that was collected and then export it over to one of the backends of your choice. So if you think about the state before OpenCensus, you probably could already use some systems for metrics collection, for traces collection. You still want to continue to use that, but the gain that you get from OpenCensus is that you can instrument your code one way, no matter what language you use, because the API are identical. And then you can decide where this information is going to be exported. And then you can change, if you want later on, to export it into a different location, but you don't need to instrument your code all over again. Not with traces and not with metrics. Finally, we came up with this notion of collector for smart traces and metric segregation, and I'll show it later on in the demo. Now, who is behind OpenCensus? Originally, OpenCensus came up from Google's internal project called CENSUS. This is used for, as you would imagine, traces collection. And Microsoft came up with very similar ideas, so we just joined forces, and some other folks out there in the observability space joined this effort as well. So we have pretty vibrant community that has monthly meetings where we try to progress together. It's all open source, so you can join as well. So it got a lot of support. It's also not featuring all of the folks that joined recently, such as Dynatrace. And basically just growing almost on a daily basis. Now, speaking about OpenCensus in C#, you probably want to know about what NUGET packages are available for you to be able to instrument your code for traces and metrics. So there are like over, I think, 15 packages available today for different exporters, for the core implementation, but these 4 are the core that you probably want to know about so that you can start using OpenCensus. So the first one is OpenCensus.abstractions, which implements the interfaces, which is basically the spec of OpenCensus, which is identical between different programming languages. Then we have the OpenCensus package, which implements these interfaces. Then, if you use HTTP client to make outgoing HTTP requests and you want to instrument this request with traces and metrics, you can use OpenCensus.collector.dependencies. And finally, we have OpenCensus.collector.ASP.NET Core, which is for instrumenting your ASP.NET Core applications. We also plan to ship gRPC package if you use gRPC for your remote procedure calls. It is also going to be possible to instrument your gRPC calls from the client to the server and back with OpenCensus, and it's in fact already supported in some other languages. Okay, so let's start talking about how you actually do get started with OpenCensus for tracing. So when you start with instrumenting your code with traces, you first need to figure out what's the architecture. And typically, there are 2 ways that it can go. First is agentless, where you have your service running in a process. It could be hosted on container, it could be hosted on a dedicated VM. And then your application emits some traces as a result of incoming HTTP requests. And then there is some exporter component which lives in your process, which basically collects those traces and send them over to some external system. The other option is using the agent. So with the agent, you have your application up and running. It could be also running as a separate process. But then the agent is installed side by side, like a separate process. It has its pros and cons compared to the agentless. For example, you need to deal with agent installation, which may not be straightforward in every environment. But at the same time, your application is kind of transparent to tracing. It just emits the traces without knowing who will collect that. And you don't need to install any dependencies in your application for being able to collect those traces out. So what we'll do, we'll get started with OpenCensus in the agentless world, and then we'll kind of gradually move forward to this other option as well. Now, before we actually see the code, we should agree on the terminology. So with OpenCensus, we have the trace, which is basically a collection of spans. The span is the basic activity that happens as a result of the incoming request. So in this case, you have messages, auth, cache.get, mysql.query, and so on as separate spans. All this together constitutes one trace. Then you have sampler, which is a component which decides whether a given trace should be sent over to a backend or not. We'll see the importance of this component later on in the demo. And finally, we have exporter, which is a component that actually sends all these traces that were collected locally into some backend system for tracing. Now, in order to get started, we need to configure those components that we just spoke about. So first is exporter. In my first demo, I'm going to use Zipkin, which is an open source tracing system originated at Twitter. So I just create the exporter, passing the exporter options, which is the service that this trace represents, and where this endpoint that collects the traces is located. Then I pass, this is tracing.export component, is OpenCensus component, which basically stores all these traces locally before they are sent over to some backend of your choice. So after we have the exporter set up, we need to set up the sampler. As I mentioned before, sampler is a component that decides whether given trace should be sent over to the backend or not. In this case, there are multiple ways to define the sampler. I'm using configuration here. So the actual sampler setting is here in the samplers.alwayssample. OpenCensus library provides multiple default samplers that you can use, such as this one, which samples every single request for mostly learning purposes. You could also implement your own components. The framework is very flexible, so that you can just implement the right interface, which is defined in OpenCensus.abstractions project, so that when you set the sampler, you can pass your own sampler that just implements the right interface. So once you have the sampler, you get a hold of the tracing.tracer, which is this component that actually creates the traces. And finally, you start creating the spans, which actually produces this instrumentation that we want to get from the demo. What I recommend is always trying to use a scoped span, which means that we're not only creating the span, but we also limit the start and end time for that span to the using statement where it is defined. So once this using statement completes, the span will close, and so we have a pretty well-defined duration. Okay, so let's see this in a demo. So I'll quickly go through some of these components that I just mentioned, and then we'll just execute this demo and see where is it traced. So this is the exporter piece. We define the exporter. We also updated the configuration to use the sampler, which always samples. You see this implements iSampler interface. You could provide your own. And then we have this tracer that we can use. We created scoped span, which is called main. And we do some operation which will happen in the context of that main span. And if we go into this do work, so we can do some stuff there as well. So I get this tracer in there as well, and I can create even subscope and subspan. So basically this span will be a child of the previous span. So you can see here we just create another span, and I can, at any point of time, get the context of the current span where I'm currently running. And I can also do some annotations, basically provide some additional metadata about the execution of the current code path. One of the possible reasons to do that, if you want to add some contextual information, for example, the name of the table, when you want to trace some activity that happens in that table. So that could be really useful information to have. So let's try to run this demo really quick. Now, I run all my demos in Docker containers, so in order to reproduce the same thing on your machine, you will have to install Docker for desktop. And also, all these demos, as well as the presentation, will be available later on. I'll post it on my Twitter, and the demos will be available on GitHub. Okay, so we just executed something which should have produced some traces. So let's try and see how it looks like. So this is Zipkin, and this is our service that we initialized. And if we find traces, we can see that it generated something. And you can see here all these activities of do work that happened within the parent activity of main. And all those things together, they constitute one trace and one single transaction that happened. I can also double-click and get these annotations that I added in my code. So this is like a simple getting started with tracing. And I could also switch this Zipkin implementation as my tracing backend to something else, like we'll do in other demos. Wait. Okay, so we saw that it's kind of easy to get started with tracing, but there are some problems that we need to deal with. For example, context propagation. When you get a lot of requests that come in parallel into your system, you want to essentially reproduce the full picture of what's going on with every single request. So that at the very least, you need to be able to propagate the trace ID that is associated with the parent of all this of every single request, as well as all the spans that happen as the sub-activities of that request. And so these spans can span across multiple components of your system, such as here you can see the front end talking to checkout, talking to email service. You want to get this entire activity tree reproduced as a trace in your system in something like this. So for that, you need to be able to pass some information. Some of that information could be just handled by the system, such as the trace ID and the span ID, but you may also want to pass some additional information, some context that should be available in your other components. For example, from the front end, you might want to send some additional information in the traces to the checkout, and then use that information to make some more decisions. So we need to deal with context propagation. Could be very useful in scenarios of A/B testing when you really want to know, when you get from the front end to the checkout, whether you're executing version A or version B on the checkout, because the whole activity started probably from version A on the front end. So it could be really important to know. So for that, we have the implementation of W3 standard that was proposed jointly by folks from Microsoft, Google, and Dynatrace. And this standard is currently in the last stages of approval. And I'm not going to delve too much into its details, but there is a link in the slides that you can go and read it. What's important is that this standard is already implemented in all OpenCensus libraries across all the languages. So if you go with OpenCensus for tracing your applications, you can be sure that if you call some external components which also comply with the standard, you will get more visibility into those components just naturally by the fact that you use the same standard for context propagation as they use. Okay, so far we were talking mostly about the tracing, but OpenCensus is also about metrics. So let's see what we can do with metrics. In order to see the demo for metrics, we need to come up with the object model which works for metrics as well. So this is the example from Stackdriver. This is Google's product that allows you to do monitoring tracing, performance, and debugging. And I just want on this picture to kind of explain some of these concepts that we will see in the code later on. So first thing, if we want to measure something, we need to define that entity of what we measure. So in this example, it's CPU utilization. It also should include the unit. So it could be percentage. It could be just one, like a unit. Could be other things as well. Then when you want to measure CPU utilization, you probably want some additional contextual information to understand where it was measured or some other stuff that will help you then break it down in the reports. So in this case, we might want to record the instance ID, maybe also environment information, so that you can then see what happens on a given machine as opposed to environment, as opposed to maybe entire cluster. Later, we'll probably also need to actually take those measurements. These are the points that essentially you see on the graph. So these are called measurements, that they belong to a given measure, and you took these measurements at a given point in time. Now, the graphs cannot represent always all the measurements that were taken, because maybe the graph represents only what happens every second. So there is a point per second here. But at the same time, you could have taken maybe 50 measurements in 1 second. So there should be a way to represent 50 different points in one point in the graph. So for that, you need what's called aggregation. Aggregation is a method that basically takes all your measurements for a given period of time and produces one point which represents all those measurements together. So this could be sum of all those points, the minimum, the maximum, distribution, or some other way for you to kind of decide on a single point to represent. Next thing that we need to cover is view data. So view data is basically taking all these measurements and also providing the values for all those things that we mentioned before, such as tags, the actual values for tags for every single point in time that we measured, as well as the values for aggregation. You can see view data as basically all the information that actually gets collected for your metrics. And then there is the view. In this case, view is just a definition of what we intend to collect. So if you compare view and view data, it's like table schema and table data. So view, it's like a table schema. It defines what you want to measure, so it has a name, but it also has this measure, tag, and aggregation definition, what you intend to measure. And then the view data is the actual measurements that you take given this definition of the view. Now that we have that, we can go into the demo. So in this demo, I'm going to export information into Stackdriver. And I could as well export it to Prometheus, which is open source system for metrics collection, or some other system which is commercial. It's just as easy. So in this case, I'm using OpenCensus exporter Stackdriver, as well as OpenCensus.stats, which is the namespace for metrics collection. Metrics and stats, it's basically the same thing as far as metric collection goes. Okay, so first thing that we need to do is define what we measure. So this happens here. I want to measure something that I called it full execution size. This is description, this is the unit. Then I want to define what additional contextual information I want to send with that measurements. So we have environment and machine. These are just the keys without the actual value. So it's like defining the schema for your table without actually sending the data for that schema yet. So we define that every measurement should have environment and machine name attached to it. And then when we actually want to send those measurements, we want to calculate the actual machine name and the actual environment name. So I created this context object, which maps between the tag key to tag value. So I just created here this is my test environment, and I'm sending the actual machine name. Now, next thing is stats recorder. Now, stats recorder is the component that stores all these metrics locally before sending them over to some backend. So we get hold of this stats recorder. And now we need to configure where this information essentially will go. So I'm using a Stackdriver exporter. And in order to use that, you need to provide the project ID of your Google Cloud project where all this data is going to be stored. And again, if you use a different exporter, it will be similarly in a way that first you provide some contextual information to kind of set up that exporter. For example, the endpoint where all these metrics will be collected. And then you need to provide what is called the view manager, which holds all those measurements locally before they are sent over to the backend of choice, which is Stackdriver here. Now we need to define the view. View in this case is defined like this. This is just the name and the description. This is the measure that we defined earlier. This is the aggregation function that I'm going to use. And these are the keys that I want to send with each measurement. I need to register that view so that the local component knows what to expect when the information is coming. Now I'm just executing something in a dedicated thread. And basically what I want to do there is a method, some random method that I implemented. And that method will just draw a point on a console just for simplicity. And every time the method is executing, I want to record the metric which counts the number of executions. So the way to do it is just getting the instance of what's called stats recorder and creating the measurement and the actual value for that measurement. So this is the number of invocation. This is the measurement that we defined in the first step. And 1 in this case is the actual value for that metric at this moment in time. And once we decide to record that, we also need to provide all this contextual information, which we already pre-calculated and put in the tag context. Now, I realize that you might see a lot of different steps to do something relatively simple. And the reason I'm showing so many steps is because this is basically what always needs to happen under the hood. A lot of those things, such as setting up the exporter and making sure that you can set up the views in a much easier way, it's all going to be abstracted away by the implementation of our C# library so that you will work less but achieve the same things. But I think it's really useful to see how all those things look like when you want to get started literally from zero. So when I execute this application, what you will see is some points starting to show up. Every point means that the foo method was executed. And what should happen behind the scenes is that we keep recording all those invocations as a metric. And then the Stackdriver exporter component that works as part of our application, it will take all those measurements and then periodically send them over to Stackdriver backend. So if I go to Stackdriver, and we are going to do that right now. I should expect actually to see that it should show some graph that represents this metric that I just collected. So I'm just going to choose monitoring, which is the Stackdriver monitoring part. Stackdriver consists of many sub-products that deal with all types of observability problems. So in this screen, basically, what I should choose is Metrics Explorer. So we send metrics to Stackdriver, and I should expect to see my metric feature here in the list, and it was called foo something. Let's see, sample execution count. That's the name. Okay, so what you should start seeing, there is this blue line. And if we leave it for a long enough period of time, you will see that it starts progressing kind of towards that side, because essentially all these measurements are taken as we speak, and the interval at which the Stackdriver graph is updating is 1 minute. So it sends obviously more than one measurement. So over time, you will see that this graph will start changing, and basically it will kind of demonstrate that we actually take the measurements and send them over. Okay, you can see now that there was some change, and if we keep this working, it's just going to basically evolve as we speak, because the method gets executed in a dedicated thread at some random intervals, and this is why the actual measurements of how many times the method was executed at given moment is going to change accordingly. Okay, so let's stop it. Okay, so let's talk about some other OpenCensus related topics. So one of the latest concepts that we introduced is OpenCensus service. OpenCensus service consists of two components, agent and collector. Now, the reason that we came up with this proposal is that some folks told us that they prefer to send information not necessarily to one exporting component, but maybe to multiple exporters at the same time. Also, they want to be able to switch the exporters without restarting their service. On production, it could be really costly to restart your running application if you just want to send the monitoring data to some other component of your choice. So we came up with this OpenCensus service solution, where basically you have this OpenCensus libraries in any language you want to use it. And then the libraries essentially will use OpenCensus agent as their exporter. So you will not have to use different exporters directly in your code. You will use OpenCensus agent as your exporter. Agent, in turn, will send information into OpenCensus collector. So basically, it means that you will need to install OpenCensus collector as another component. Now, OpenCensus collector could make a decision what to do with those traces instead of the agent making the decision, and instead of you making the decision in the process where your application is running. And then if you want to add more exporters, you want to export to multiple observability backends, basically you need to deal with OpenCensus collector. There is a YAML file where you can make your configuration changes, and then if we need to restart the component that sends information to the right backends of choice, you just restart the OpenCensus collector, but your system is not impacted in any way. So this is maybe slightly more sophisticated architecture in terms of what you need to install, but it has some benefits, which is also includes smart sampling that I'm going to mention shortly. Okay, so we mentioned this concept of sampler, which is the component that needs to decide whether to take this trace and send it over or not. Now, traces can be multiple. Like your application can generate a lot of traces, and those traces could include many spans. And if all this information is exported to some backend of choice, you could pay a lot of money for that. So obviously, you don't want to overpay. But also, even if you put the pay aside, you can create a lot of noise, because if there are some activities which always succeed and you trace everything, you don't really need information about something that always works. So you probably want to skip all these unnecessary traces and only capture what you really care about, reducing costs and also reducing the noise. So we came up with a solution to solve that, which is smart sampling. And there are two ways that you can do sampling with OpenCensus, or in general: head-based sampling and tail-based sampling. Now, with head-based sampling, the sampling decision is happening when the request comes in. So request comes in, there is a component which is that sampler that we saw before in the first demo, and that component decides whether to take that trace and send it over or not. Which could be nice because we could just decide to use sampler, which takes maybe some probabilistic approach, like take 10% of requests and sample only them, or take requests that match given criteria, and then this way just reduce the cost. But in some cases, there could be a problem where there was a decision to trace, but then it's not interesting trace. The other problem that could be is that request comes in, we decided to not trace that because it's not in this bucket of 10% that we do want to trace. And then basically the downstream systems where this trace goes through, there is a problem. And so you will miss this trace because you took the decision early enough. What we really want to do is take the decision when we have all the information. And this is where tail-based sampling can really help you be more efficient. So I'm going to show the tail-based sampling. And for that, I need to do some warm-up for my demo. So I'm going to start. And while it's starting, we are going to talk about the architecture of this demo. So this demo is based on a sample app that we created at Google called Hipster Shop. There is a repo for that demo in the GitHub, and you can also see it. Basically, it's just an e-commerce application developed using the modern cloud stack. And there are multiple components which are all developed using different programming languages, and they are talking to each other. One of those components is checkout service. So when you hit the front end of this Hipster Shop, you may want to click on checkout and do the actual operation of checking out and buying something. And what we want to do in this demo is basically simulate what's going on with traces when this checkout activity is not always succeeding. So what will happen is this. There is a component that we created that simulates creation of the loads to Hipster Shop application, such that some of the activities will include errors in the checkout component. Some other activities will just succeed. Okay? Now, we are using here this OpenCensus service, and the collector, when it gets all these traces, it has to take the decision of whether to trace all these activities that happened in Hipster Shop or not. In order to demonstrate that tail-based sampling is really an effective way, we actually try to export the information to two separate trace backends. In this demo, I'm going to use Jaeger, which is another open source tracing system just like Zipkin, but this one was created by Uber. And basically, the first instance of Jaeger is going to use head-based sampling, which basically means that it will take the decision whether to trace or not at the early stage, so you can expect to see different types of traces, both with errors in the checkout as well as without errors in the checkout. And the second instance of Jaeger is going to use the tail-based sampling, where we only trace activities where spans have errors. Okay, so let's see it. Okay, so it's warmed, and it's all running in containers. You can reproduce it anywhere, and the instructions will be posted on GitHub alongside this presentation. So I'm going to open the first instance of Jaeger. And here are all these services of the Hipster Shop. One of them is the checkout service. Oh, did it click? Okay. So when I look at the traces for the checkout service, or that involve checkout service, you can see that there are mixed traces. Some of them don't include any broken spans or spans with errors. Some of them do include spans with errors. Okay, so it's really mixed because the traffic in some cases simulates errors, in some cases it doesn't simulate the errors. If we go to the second instance of Jaeger, let's do it here. And we also open the traces. You see much less traces, and every single activity that was captured here that involves the checkout, it also involves some errors. So basically, given the same volume of trace information that came into the collector service, in this case, we were able to collect much more important information first because we use tail-based sampling, where we only sample the cases where errors happen in our spans. Okay. Some more concepts that OpenCensus introduces that also originated at Google. zPages. So at Google, what we have in some internal systems is the ability to understand on the given machine when the traffic hits that machine, what traces are captured on that specific machine. So basically, you can just go into /trace_z or RPC_z, depends on what type of communication framework is used with that machine, and get all this information because it's actually something that is hosted in the library that we use for instrumentation. So you just get it kind of for free by mere fact that you instrument using OpenCensus libraries. Now, it's not available yet in C#, but it's available in Java, Go, and some other languages, and will be available in C# as well, just like any other functionality. So you will get this just by using the right instrumentation libraries. Now, we have the metrics of what exporters are available. T is for trace exporters, S is for stats or metrics exporters across different languages. Now, you see that it's not full, and we are working on improving that across all different languages that we want to support, as well as major backend components for observability that want to have their presence in this OpenCensus ecosystem. But it's improving literally on a daily basis, so we'll get there, and it will be fuller as we progress. We also have some existing pre-built integrations. So if you use one of these components, and this is not the full list, basically these are already pre-instrumented with OpenCensus. So if you depend on these components and your stack is already instrumented with OpenCensus, you will get visibility not only into what your activities are doing, but also what these external components are doing, because they implement the same trace context propagation, and they also provide you some of these metric views, which are already kind of pre-built by folks that created these integrations in the first place. And of course, we want to improve this and build more and more integrations. One of the interesting examples is Google Cloud. Basically, just by mere fact that you run in Google Cloud, we will detect automatically all these tags that represent the environment where you are running. So we can detect that you are running on Google Kubernetes Engine or Google App Engine or some other environment, could be just VM, and attach these tags into every single span that gets created, so you will get a lot of this helpful information without doing anything. Okay, so OpenCensus has pretty active community. We have this opencensus.io website, Gitter channel. We develop in multiple GitHub repos. It's basically divided by different languages that we support. So take a look. I hope that you can also join and help us improve and progress. The community meets once a month. It's a public meeting that you all can join. We have pretty substantial improvements in the last year, 2018, and we want to do even more in 2019. One of the main focuses that we are going to work on this year is improving the ease of use. As you could see in the second demo of the metrics, there are a lot of steps that you need to do to be able to accomplish relatively simple tasks. We want to reduce that so that you almost don't need to do anything and you will still get a lot of information and insights from your system if you instrument it with OpenCensus. We also want to enhance the feature set across all different languages that we support so that there will be no gaps in functionality between the languages. You can use in any language you want. Building strong community. CNCF is one of the directions that we want to go. Maybe trying to accept this project into CNCF, as well as you might heard about open tracing, which is another try to kind of standardize on how do you do tracing across the industry. They share a lot of very similar goals, but they only cover tracing. Whereas OpenCensus covers metrics and also logs in the future. So we want to basically get together and make sure that there is one standard that works for all and progress over there. So I encourage you to give it a try and join the work. And with that, I'd like to thank you. And if you have any questions, I'm here. All right, thanks. Yeah.
I think it seems really great. Looks like it does a lot of stuff for you, and you don't have to think too hard about setting it up. But in terms of when you have set up all your traces, do you have any recommendations for how to make that as simple as possible? It seems like you might have to set it up in quite a lot of places.
So.
Sorry, that's quite an open question.
Yeah, it really depends on what stack do you use and what circumstances. For example, if you develop in C# and use ASP.NET Core, so you can plug your tracer into the dependency injection of ASP.NET Core, and then you have this iTracer available everywhere, so you can just use the iTracer.create new span and take it from there, basically just one API call to create the trace. Also, we are planning to have the basic HTTP operations as well as gRPC operations already pre-instrumented. So all you will need to do is just to say something like add OpenCensus extension method, where you just say, how do you want to sample that? Who is your exporter? And we'll take it from there, basically. So every incoming request into your ASP.NET Core application will be automatically instrumented, so we'll create a span for you. The name of the span will be as the name of the request that is incoming to you, like /messages or whatever. And then if your code is making outgoing requests and you use, be it HTTP client or you use gRPC client for making outgoing RPC calls, we will also instrument that as well. So you just create those clients in advance once you register all your components in dependency injection. And once you get that instance through dependency injection, it's already pre-set up with tracing, and you can also do the same thing with metrics. So basically, the majority of the common stuff you will be able to do maybe like with 2 or 3 lines of code at the startup time when you just say who is your exporter and how to sample that. But if you want to do something more, because with traces, you're not only limited to tracing the HTTP stack, you can also trace some logical activities that happen in your application. So it will also be like one API call away. Okay.
So the span, can it, span, I suppose, is the word, different components in your whole architecture. So let's say if you've got your web services calling to another component on a different machine, and they can all you can follow the trace from one component to the next component to the next component. So when it goes wrong, oh, that was the source.
Yeah.
And this bit was a bit flaky in the middle, which caused the bit at the end to go wrong. Is that the idea of the span, that it spans the
Yeah, so
whole-
basically the trace is your end-to-end activity. So say someone makes a request to google.com, and basically this triggers the start of the trace, but then there are a lot of internal systems that are involved in producing that response for you. So you can think that every system like that will produce at least one span which kind of describes the activity of that subsystem. So when there is incoming request to that subsystem, it basically starts the span. It does whatever it does, and then when it finishes, it ends the activity for that span. Now, all those spans are sent to the tracing backend, as since every single span includes the information about the trace ID and the parent for every span. Only the first span doesn't have a parent, which is the initialization of the full transaction. So basically, you will get all of this representation of what's going on in the tracing backend just because they all follow the same object model. So all these tracing backends will be able to represent that in the same way, more or less. Okay, yeah.
You mentioned that OpenCensus supported HTTP and gRPC.
Yes.
We use Rabbit and Kafka as well. Do you plan on supporting those? And if not, how would you recommend? What's the best way to integrate message brokers with such a system?
So I think I'm not sure if it's already supported, specifically Kafka, but I think there is a plan to support it just like any third-party integration. So we do want to be able to instrument all those things in a way that you just declare in your code that I do want to get those traces, or I do want to get metrics from those external systems, and it will just happen. And you will have a spec which defines what you should expect to get, especially for the metrics. I can give example with gRPC and HTTP, but it should hold the same with all third-party integrations. For example, if you want to measure the quality of service of incoming calls into that third party, there is a view definition that will say what are the metrics that will be collected by this third-party component. So if you enable OpenCensus metrics for that component, there is some implementation that you would be able to find through this OpenCensus ecosystem, but that implementation will just guarantee that these metrics get produced for you, and you just define where you want to send these metrics, what is your exporter, and you will just get all that information and be able to create the graphs, even though it's external component for you. So even if it's a message broker, yes, we still want to take care of that. Okay. Cool. Thank you.
Thank you.
How do you get the smiley faces on your Google Chrome, by the way?
So it supports profiles. So you can have work profile and personal profile.
This is your token of thanks from the NDC.
Oh,
It
thank
goes
you.
to a charity that they support. So
Nice.
thank you very much.
Thank you.
Just one last question. Just one last question.
Yeah, sure.
You mentioned .NET Core. You don't support .NET Framework, do you?
So actually we do.
Oh, you do?
Yeah, so we do support even, it may sound a bit weird, but we support starting from 4.5, which is not officially supported by Microsoft. And the reason for that is that Microsoft folks said that a lot of people still use 4.5, and they don't want to lose those people because essentially the story is you use something old which may not be supported, and in order to migrate that into something newer, you at least want to get the visibility on what it's doing right now, and then start your migration story. So this is why they want to provide this observability into slightly older stack than what they officially support, so that you can get started with a really good picture and just move forward.
That's exactly the case we've got this component which was kind of written just at the beginning of .NET Core. So actually it was started in .NET Core, the libraries weren't ready, so we wrote it in the .NET Framework. and now we just want to add some, like, it's quite big, so we do want to move it to .NET Core eventually, but we need some monitoring and observability kind of right now.
Yeah, so it is definitely supported now, but the only caveat to that is that not all the exporters have support for both .NET Framework and .NET Core.
Does Prometheus work? Do you know off the top of your head?
It works, but I mean with .NET Framework, the regular one, but I need to double check if all the specs for Prometheus work. Like I remember there was a recent bug like from a few weeks ago where if you want to host Prometheus exporter, there is this way of like exporting your metrics so that Prometheus can grab them, and it uses port. So in some cases of Azure websites, they may not allow you to export a separate port, so you need to export it on the same port as your application. So there were some folks working on fixing that. So in general, it's supported, but we need to see the details if it really matches your use case.
Well, I definitely give it a look. Thank
Okay.
you very much.
Yeah, sure.
Great talk.
Thanks.
Thank you.
Okay. Thanks. I hope that, I mean, I felt like it started not well, but then it progressed better.